in the last lecture, we saw that inside a material there are three processes which take place, namely the spontaneous process, the stimulated process and the absorption process. And then we saw that the stimulated process takes place on its own. So, if the electron is there in the higher energy state, then naturally it has a tendency to relax to the lower energy state, and in that process the photon is released, which we call as the spontaneous photon. Then the two processes which take place in the presence of a photon, that is the absorption process, that is when the photon is incident on the material, the photon is lost, an electron makes an upward transition. In the other case, this photon may stimulate a downward transition of the electron, and in that process we have two photons which are emitted, and these two photons have same properties as the original photons, or in other words these two are the coherent photons. And then we saw that this process is more like a multiplicative process, because one photon can create two photons and then two photons can create further photons and so on. So, once this process starts taking place, the spontaneous emission does not have much scope to show up, and that is the reason in the following discussion we essentially concentrated only on two processes. One is the absorption process and other one is the stimulated process. And then we quantitatively wrote the equation of the growth of the photon flux as a function of time. We also saw that inside a material the probability of an upward transition and downward transition in the presence of a photon is equal. That means, when the photon is incident, we cannot predict whether this photon will get lost, an electron will make an upward transition, or will the photon stimulate this process and ask this process to emit one more photon. And then we saw that if this process has to dominate, then we should have more electrons in the upper level, and then we saw some 3 energy level systems and 4 energy level systems and so on. And from there we concluded that we can manipulate the energy levels and the lifetime of the electrons in different energy levels, so that there is net what is called population inversion. That means, there are more electrons in the upper state compared to the lower state, and then in the presence of a photon the stimulated process will start, and then you will have the coherent emission coming out of the material. With this understanding, then we wrote the equation for the growth of the photon, and then we said the rate of change of the photon flux, that is now difference of the downward transition and the upward transition. So, this is the probability of the transition, this is the density of the photon flux, and N2 and N1 are the electron densities in the upper and lower energy states. And then we also had found out from the black body radiation that this quantity B21 can be written like that in terms of the lifetime, what is called the spontaneous lifetime. And then we saw that when the photon is there inside the material, it is not stationary, it moves with velocity of light. So, therefore, we have a distance travelled by the photon, which is velocity of light inside the material, which has a refractive index n multiplied by t. So, we could convert this equation, which is with respect to time, in terms of distance x. So, the equation was converted into this equation, which was further simplified to get an equation which was this. So, we had a differential equation for the photon flux as a function of distance, which could be written as some constant g multiplied by the photon flux. So, this says that the photon flux grows exponentially or decays exponentially depending upon sign of this g when it travels inside the material. And then we saw three conditions, that is, if N2 is less than N1, then this g is negative, then the photon flux essentially exponentially dies down as it travels inside the material, and this quantity then one can call as the attenuation constant. So, G will be negative. So, G is equal to minus alpha. Whereas, if you are having N2 is equal to N1, then the photon flux which is incident on the material, essentially the same number of photons come out. So, not that internally nothing has happened to these photons, again some photons got absorbed, some photon got emitted and so on, but the net photon flux which is coming out is same as the net photon flux which was impinging on the material. This condition then we call as the transparency condition. So, in that process the G is 0. So, photon flux neither grows nor decays when it travels inside the material. And third condition we had is if N2 is greater than N1, which is the condition for population inversion, and that is what we are interested in, then G becomes positive and then the photon flux grows exponentially inside the material. So, what that essentially means is that as the photon travels more and more inside the material, and if the population inversion is maintained, then the photon flux will go on increasing exponentially. So, now at this stage essentially we want to now create a mechanism by which the photon can be made to confine more and more inside the material, and when it travels more and more inside the material, its number of photons grow. So, essentially we have a growth of radiation, which is the coherent radiation. Before we get into that aspect, let us look at this quantity here, which we call as the gain coefficient, which is this. This depends upon firstly this quantity, which is the frequency. It also depends upon the spontaneous lifetime, which is tau sp, and it also depends upon the refractive index of the material, and of course, the population inversion, which is N2 minus N1. So, if you want to write explicitly this quantity gain coefficient G, this is proportional to 1 upon f square. This quantity is also proportional to 1 upon tau sp, and it is proportional to the population inversion, which is N2 minus N1, and is proportional to 1 of the refractive index square. Since the refractive index square is nothing but the dielectric constant of the medium, the gain is inversely proportional to dielectric constant of the medium. But if I look at now these parameters here, what we find is for the given parameters like population inversion and spontaneous lifetime and so on, the gain is inversely proportional to square of the frequency. That means lower the frequency, higher will be this gain. Or in other words, what that means is that a system can be lased very easily at low frequencies compared to the high frequencies. And that is the reason creating a laser at low frequencies or longer wavelength is relatively easier than making the lasers to operate at low frequencies, high frequencies or shorter wavelengths. So, later on we will see that when you are having material which are having various energy levels, and if the population inversion is created, then longer wavelengths will have a tendency to lace faster, and once they start lacing, essentially the population inversion which is created get diverted to the amplification of the longer wavelength signals. The second thing to be noted here is that the gain is also inversely proportional to the spontaneous lifetime. That means shorter the spontaneous lifetime, higher will be the gain. What that physically means is that if the tau sp is small, that means the electrons are naturally willing to jump down. Even if this stimulated process was not there, it would have jumped down because of the spontaneous process, because tau sp is very small. So, electron is eager to make a transition which is downwards, and which makes this stimulated process easier. So, you get a higher gain. But at the same time, if the electron is willing to jump down even without the presence of another photon or without stimulated process, that means you will have a lot more spontaneous emission which will be coming out of the system now. Or in other words, lot more electrons are going to make downward transition, or population inversion will deplete very fast. So, you have to keep replenishing the electrons at much faster rate if this quantity is small. But by doing this, essentially we get the higher gain into the system. Then of course, we have the gain proportional to the population inversion, and it depends upon the dielectric constant also. So, at this stage then one can now say that if electron makes transition, if there is a population inversion, then depending upon the frequency and the spontaneous lifetime, the photon flux growth will change inside the material and the radiation will grow exponentially as it travels inside the material. So, up till now essentially we were seeing this whole process, the stimulated process, as the amplification process, and in fact this process is an amplification process. So, if you recall, when we started discussing this process, we said this photon which comes here, it triggers this transition down. This whole process is stimulated by this photon which is incident here. So, if this photon is not there, then of course, this process will not get stimulated, and there is no question of these two photons getting generated. There is no question of stimulated emission. So, when we are trying to use this system as an amplifier, that is what principally laser is. It is a light amplification by stimulated emission of radiation. Then this photon is supplied externally, that is the photon which is to be amplified. That is the optical signal which is to be amplified. But when we are discussing now this source laser, we want this laser to generate light. For optical communication, of course, we may use laser for amplification, but at this point of time we are looking for an optical source. So, what that means is that now this photon which is going to trigger this process is not going to come from outside. If the photon does not come from outside, then of course, this process cannot take place. But if you note that if the photon was not present here, and if you create population inversion, that means if you create more number of electrons to the upper level, then naturally this will make a transition and this photon will be emitted. Once this photon is emitted, now the photon is available, and this photon now can trigger a process which will be stimulated process. So, even if one transition takes place here, the photon is going to be emitted, and now this photon is capable of starting this process which is the stimulated process. But what that means is now that the seed which is coming for the stimulated emission is internally generated due to spontaneous emission. And since this process is only an amplification process, what are the characteristics of this photon which is created by the spontaneous emission? They are going to be reflected into these photons also, because this process is essentially creating more number of photons which are having same characteristics as the original photon. Now, this photon which is making, because of this transition here, is an incoherent radiation, because this photon which are because of the spontaneous emission, they do not have relation with respect to each other. So, they do not travel in the same direction. There is no special coherency between these photons. So, you will see that if these photons were not spatially coherent, even the photon which are going to be emitted here will not be spatially coherent. So, if the seed has to come from inside, then the emission which you are going to get, even because of the stimulated process, will not have the spatial coherency. Temporal coherency will be there because we are talking about very sharp discrete energy levels. Later on you will see that the spontaneous process inside a material like semiconducting material, these bands are not sharp, and then this photon also will have a spectral width, and then we will not have even temporal coherency into the stimulated emission. So, first thing what we note here is that since the seed is coming from inside, though amplification is going to be there and number of photons are going to be large, they will not have complete coherency. But the same problem we had in other amplifiers also. When we talk about electrical amplifiers, when we have an amplifier, we can always convert an amplifier into an energy source which is called an oscillator, and there also the signal is generated internally because of noise. Then if you want to create the coherency, which electrical signal, which means creating a sinusoidal signal from an oscillator, what do? We essentially get that output signal and have a frequency selective feedback. So, the photon which are generated, which are of random nature, which are of spontaneous nature in this case, they will give you amplification. And now, if we make sure that all the photon which are going to come here do not get amplified, but very selectively the photons are fed back into the system. So, the gain is selectively for certain frequencies, then essentially the coherency into the system is increased. So, the first thing what we have to do is we have to create some kind of a frequency selective mechanism, so that the coherency into this radiation can be increased in the system. Now, coming to the semiconducting material lasers, if I look at this expression here, which is the gain coefficient, this quantity, leave these all parameters here, the spontaneous lifetime, which will become the non-radiative or recombination lifetime here. This is the frequency which will depend upon the band gap of the material, but the quantity here, which is N2 minus N1, this is nothing but the injected carriers in the PN junction under the forward bias condition. So, if you inject the electrons and holes inside the junction, then this quantity N2 minus N1 equivalently means that I have electrons and holes available for recombination, and this can recombine, and once the photons are generated because of this spontaneous recombination, then these photons can trigger the stimulated process, and there will be much faster recombination would take place, which will give the stimulated emission. So, this quantity here N2 minus N1 is exactly same as the product of the electron density in the conduction band and the hole density in the valence band. And we have already seen that this quantity has a spectral distribution, which is nothing but the LED emission. So, now what we find is that this quantity here N2 minus N1 which we have, it has a spread in the energy, and this exactly is same as what we see for the LED. Or in other words, what we are saying is that this quantity here gain which we are talking about, now that is going to have a shape which will be similar to what we have seen for the LED spectrum. So, the gain function essentially goes as what we have seen for the LED. So, it has a variation which goes something like that. this is now going to be the gain variation, because this function essentially is controlling this quantity here, which is n2 minus n1. But since this quantity here g is now riding on the exponent of this, if I write down the spectrum of this photon flux as a function of frequency, that will be much sharper compared to this, because now this is not the spectral distribution of the photon flux. Photon flux has a spectral distribution which is e to the power this quantity g. So, we get a photon flux distribution which will be much narrower like this, or in other words, the spectral width of this is going to be much smaller compared to the spectral width of this. So, first thing which we had noted for LED, that LED has very large spectral width, and which is not very good for optical communication because it gives large dispersion. We now see that if we take the same semiconducting material and trigger the stimulated process inside this, then the spectral width of the photon flux will reduce considerably, because this function here now is going to ride on an exponent. So, as we have seen, this spectral width for LED was typically of the order of about 70 to 100 nanometer, whereas if you go for the spectral width of a laser, then this spectral width will be typically of the order of about 1 to 2 nanometer. So, idea here is very simple now, that we take the same p-n junction, inject the carriers inside that, and when the recombination takes place, the photon which are going to be generated because of the spontaneous recombination, they will trigger the stimulated process, and if the stimulated process dominates over the absorption process, then we will have a stimulated emission coming out of this. But the spectral width of this stimulated emission will be much narrower compared to the spectral width of the spontaneous emission. So, one reason for which we wanted to go for lasers, and that was the reduction in the spectral width, that has been achieved by the spontaneous emission here. So, the same p-n junction LED, if we do some manufacturing tricks and if we inject enough current inside the p-n junction, then we can get an emission out of this, which will be having a spectral width which is much smaller compared to what otherwise it would have given. So, one purpose has been achieved in this process. Second thing now, coming to the efficiency aspect of LED, there we saw that the photon which are born can move arbitrarily in different directions, and because of that very small fraction of photons emerge out of this device, which lie within the critical angle cone, and that's why the efficiency of this device is very small. Let us now see how that has been taken care of in this process. So, as I mentioned here, if the whole process is started by the spontaneous emission, and if the spontaneous emission is isotropic in nature, then the radiation which is intrinsically going to be coming because of even for stimulated emission will be isotropic in nature. There is no spatial coherency in that. So, how do we introduce spatial coherency? And as I said, spatial coherency can be introduced by giving certain feedback. So, putting the photons back inside the system only for certain directions and making the photons leave which are not traveling in that direction. If you could do that, then essentially we have created the spatial coherency into the system. So, this is what precisely is done here. So, let us say now we are having a medium in which the amplification takes place, So, this material is excited, you have got population inversion inside this, and let us say the photon, because of spontaneous process, is created. This photon has a probability of moving in all direction equally. So, certain photons will move in this direction also. So, let us say a photon moves in this direction. Now, when the photon reaches on this wall, let us say we put a mirror on the face of this medium. So, the photon will reach up to this point and will get reflected from this. The photon will travel all the way back up to this face, and when it comes here, let us say if you had a mirror here also, the photon will come, will get reflected again and travel back inside this. So, the photon which has traveled perpendicular to these mirrors, and if these two mirrors are parallel, then the photon which are moving in this direction will come back to this location here. Whereas, if the photon is not moving perpendicular to these two planes, it will move and it will simply get lost. So, those photons which are moving in this direction, they will get lost, they will not be confined inside the medium. Whereas, the photon which is moving perpendicular to these mirrors, it will be confined inside the medium. And as we saw that if the photon is confined to the medium, it travels more distance inside the medium, and therefore, it grows in number. So, these photons which are moving in this direction, they will travel a short distance inside the medium. So, they will get amplified during this process, but after that they will leave the medium and they will be lost. Whereas, the photon which is moving in this direction will travel this distance, which is much longer compared to these photons, and therefore, will grow in numbers substantially. So, what we have done in this process, we have essentially diverted the amplification process to only the photon which are moving perpendicular to these planes. So, let us say in general case these mirrors are not completely opaque, they are not reflecting complete number of photons, because if that happens, the photons are completely confined inside this box and no stimulated emission will come out of the system, which is not of any use. So, we want that whatever photons are moving in this, a small fraction of photons should leak out, and those photons which are leaking out will have same characteristics as the photons which are confined inside this region. So, let us say if we start some n number of photons from this location, they move in this direction, let us say they travel a distance L, and then they again come back to the same location. So, in that process they have traveled a distance which is equal to 2L. Also, if the reflectivity of this mirror is given by R1 and the reflectivity of this mirror is given by R2, then the n photons which started from this location would grow exponentially, which is n times e to the power g into total length traveled, which is equal to 2L. But the part of the photons are going to leak also from here and from here. So, the photon which are going to be confined here will be multiplied by this reflection coefficient, which is R1, similarly reflection coefficient here R2. Also, it is possible when the photons are moving inside this, there may be some other mechanism by which the photon may get lost. It may recombine, it may again get lost because of recombination or because of absorption. So, we have a stimulated process which gives you gain, but there are maybe some other processes which might create a loss for the photon. So, we have a gain inside this system, let us say this is G, and we are having attenuation constant for this material, which is, let us say, given by alpha. So, when the photons move inside this, we will have the net gain coefficient, which will be G minus alpha. So, now one can say that if we start with n photons from here, after one round trip, the photons which reach here will be n e to the power G minus alpha into the distance travelled, which is 2L, multiplied by the reflection coefficients, which are R1 and R2. Now, if we want that the whole system is in a steady state condition, that means even after leaking these photons out, the total number of photons which are confined inside this region, that is unchanged as a function of time, then the number of photons which started from here, that should remain same after one round trip. Or in other words, what we are saying, n should be equal to n e to the power G minus alpha into 2L multiplied by the reflection coefficients, which is R1, R2. N will cancel. So, essentially we get R1, R2 e to the power G minus alpha into 2L is equal to 1. This is then condition for the sustained oscillations inside this region, which is same as the Barkhausen condition for an electronic oscillator. So, if this condition is satisfied, then the photon flux neither grows nor dies as a function of time inside this region. So, considering all losses inside this medium and also the partial reflections which are going to take place from the mirrors, if this condition is satisfied, then you will have the net flux of the photons constant inside the region, and also the net photon which are leaking out will be constant. So, we will have a constant radiation coming out of this system, which will have same properties of the photons which are inside this, and inside this region the photons are coherent. So, this radiation which is coming from here also will be coherent. So, intrinsically we had temporal coherency because spectral width of that was very small, it corresponded to the energy levels, but originally it did not have spatial coherency. And now by putting these mirrors here, what we have done is we have introduced the spatial coherency, because now only the photon which are moving in these directions, they get amplified, but the photon which go in this direction do not get significantly amplified. So, this emission which is coming out from here will be spatially coherent also. Or in other words, the radiation which comes from here will be highly beamed radiation. So, it will be a narrow beam in which the radiation will come out from this, because this radiation corresponds to essentially the photon which are bouncing back and forth between these two mirrors. So, this is the very important condition for the sustained oscillation inside this region. Now, when you look at the photon here, the photon up till now we were treating more like a particle, and we talked only about the number of photons and so on, but photon essentially is an electromagnetic wave. So, when we are saying the photon is moving from here and then coming back like this and going like this, essentially the electromagnetic wave is bouncing back and forth between these mirrors. So, if the electromagnetic wave travels a distance which is equal to 2L, it undergoes a phase change. So, after one round trip, even if the total number of photons are conserved, that means this condition is satisfied. But if the phase of the photon after one round trip is not multiples of 2 pi, then the photon which is reaching here after one round trip will not be in phase with the photon which is born there at that instant of time. So, these two fields will cancel each other. In other words, it will have a destructive interference. So, for a sustained oscillation, only this condition is not adequate. This condition should be there, but in addition to that, we must also satisfy the phase condition for this wave which is traveling inside this. Now, note here, this is the bound structure. You are having a bound medium here and the wave is traveling inside this. So, essentially we are talking about a propagation of an electromagnetic wave inside a bound dielectric medium, which is nothing but a waveguide. So, we have here propagation of light inside this medium, and this structure is like a waveguiding structure. And since we are putting some reflecting boundaries on the two ends of this, the electromagnetic wave is reflected from here and it bounces back and forth in this, or in other words, this structure essentially has become a resonant cavity of electromagnetic wave. And therefore, this is what is called the Fabry-Paro cavity. So, we have here cavity. So, this structure where photons are confined by putting the mirrors on two sides of this is what is called the Fabry-Paro cavity. So, now what we are saying is we are having now a waveguiding structure which is like this, and electromagnetic wave is going to move inside this, and then you are going to put the boundary conditions here in the form of mirrors which will reflect the wave. So, you will have a resonance inside the structure. Now, we know from our basic knowledge of waveguides that electromagnetic wave, when it is travels inside this bound medium, it may not travel like a uniform plane wave. It travels in the form of mode. So, it has certain distributions in the transverse direction, which is this direction, and will have a propagation constant in this direction. And as we know, the propagation constant is characterized by the wavelength of that mode inside this waveguide. So, you can say that you have now the phase constant which is in this direction, which is given by beta, and beta which is phase constant which is equal to 2 pi divided by lambda, which is the wavelength, multiplied by n effective of this medium. Now, note here we are using the term n effective and not the refractive index of this medium, because when the electromagnetic wave travels inside this, it is going to travel in the form of modes, and the velocity will not be same as a uniform plane wave in that medium. So, if we calculate the ratio of the velocity of light in vacuum to the velocity of light of a mode inside this medium, that number will not be same as the refractive index of the medium, but that number is the one which we call as the effective refractive index. So, for a particular mode of this waveguide, we have a refractive index which is given by this. So, now what we are saying is, if the length of this thing is L, and let us say you are having the mirror which are completely reflecting mirrors here, which introduce the phase shift of pi. So, we got a phase shift of pi here, a phase shift of pi here, and the wave has travelled a distance which is 2L into beta. So, the net phase change which we get in this process in one round trip, that will be equal to pi plus pi, which is 2 pi, plus 2 beta into L. And we are saying for constructive interference, this phase change must be equal to multiples of 2 pi. So, you want 2 m pi, where m is an integer. We can absorb this 2 pi on this side. So, what that means essentially is that if this condition 2 beta L is equal to multiples of 2 pi, integer multiples of 2 pi, then we will have a constructive interference, and then we can have the oscillator working and getting a coherent emission out here. So, for a coherent emission to come out or the laser to work, we should have two conditions satisfied. One is this condition, which is R1 R2 e to the power g minus L into 2L equal to 1, and second condition, which is the phase condition, which says that 2 beta L is equal to multiples of 2 pi. We can substitute now from here. So, you want a condition 2 beta L equal to multiples of 2 pi, which is 2 m pi. We can substitute for beta. So, 2 into 2 pi divided by lambda into n effective into L, that is equal to 2 m pi. Two pi will cancel. So, you will get L from here, that is equal to m into lambda upon 2 n effective. So, what that means is that the length of this cavity should be multiples of lambda by 2 divided by the effective index of the material. So, then what that means is that if the length is equal to lambda by 2, essentially we have a standing wave pattern inside this resonator. So, this is the cavity. The field has to be 0 at these two ends, where reflection coefficients we have taken as -1. So, we can have a pattern look like that. If this is equal to lambda by 2, which will be the first resonance, or we can have like this, which will be second resonance, and so on. So, what that means is, if the material has population inversion and if it has length L, then we can have many values of m which might satisfy this condition. But note here that m is an integer. So, essentially the discrete wavelengths would satisfy this condition. So, even if you are having a population inversion which can amplify a broad radiation, every frequency within that band will not satisfy the phase condition. As we have seen that the profile which we have got for the emission photon flux, which looks something like this. What we are saying now, within this band also where the amplification is taking place, every frequency cannot satisfy the phase condition. So, by and large, the gain condition will be satisfied by this profile, but phase condition will be satisfied only discrete number of frequencies or wavelengths within the spectrum. So, let me exaggerate this picture a little bit. So, if we say that the spectrum is like this, which we get because of the population inversion and all other parameters of the material, then within this spectrum certain frequencies only will satisfy the phase condition. So, a spectrum will not be a continuous spectrum for the laser emission. It will be essentially set of these spectral lines, because these are the lines which will satisfy this phase condition, here. So, two things should be noted here when we talk about an emission from the laser, that is, although we are having the population inversion which has a very large energy range, as we saw in case of LED, it gives you a spectral width of about 70 to 100 nanometer. The same population when generates stimulated emission, it has a much narrower spectral width, because that n2 minus n1, that function essentially rides on an exponent, and because of that the effective spectral width of the photon flux is much smaller. Secondly, within that narrow spectral width also only discrete frequencies will satisfy the phase condition, and therefore, even that narrow spectrum will not be continuous in nature. It will be consisting a set of spectral lines. So, then if I look at now the spectrum of this structure, this will actually look something like this. So, you see this is the spectral width which you are going to get intrinsically because of the population inversion, and these are the lines which satisfy the phase condition. So, if you wanted to make a true laser, that means if you wanted to create a single frequency or single wavelength from this laser, one of the ways is to create this cavity in such a way that only one frequency lies in this band where the gain is possible, and the other frequency lies outside this band. So, that will not get amplified. Or in other words, what we are saying is only one fundamental mode can be excited inside this cavity, and even if the second mode is not excited, we will get only one spectral line which will be generated by this laser, and which will be very, very narrow spectral line, very narrow spectral width. But if we do that, that means that the length of this cavity here should be such that even m equal to 2 should not be possible. Or in other words, the length of the cavity should be less than lambda of the radiation which we want to amplify. Now, since we are talking about the emission which is typically of the order of about 1 micron wavelength, what that means is a length of the cavity must be less than 1 micron. Now, you will note that already inside the p-n junction where the recombination takes place, which is the depletion region that has a very small length, if you make this length also which is very small, about 1 micron, then the total volume over which the stimulated amplification takes place is extremely small. So, this region cannot really sustain a very high photon flux density. So, in principle it is possible that by reducing the size of the fabric wire cavity, one should be able to excite only one line and therefore get a very narrow spectral width of the laser, whereas in practice the length cannot be very small. And in other words, if the length is not very small, many more values of m would satisfy this condition, and typical spectrum from the laser would look like that. So, by doing this, we have got significant improvement in the characteristics of radiation. We got a very narrow spectral width compared to LED. Also, as we have seen earlier, we now created the spatial coherence. So, the photons are now going to come out which are perpendicular to the mirror, and they are going to come in a cone which is very narrow. And if this cone now is much smaller compared to the critical angle cone for the material, most of the photons will come out of the system. Or in other words, we got a large efficiency for the device. So, what we conclude from here, that if we take a semiconductor PN junction and if we make the stimulated process to overcome the absorption process, then the stimulated emission will have a very large efficiency. Most of the radiations will come out. This radiation will have much narrower spectral width compared to what one would get from LED, and therefore, this source will be much superior compared to the LED for long distance communication.